Assalamualaikum, my name is Farah Zulaikha, Binti Jafrikhairi, matrix number 207785. I'm from group 3, so today I'll be presenting on our group assignment 1, which is on the differential equation in academic principle. In this video presentation, I'll be presenting on the visual arts design and differential equation. Next, the application of ordinary differential equation in molecular biology will be presented by Ahmad Haridz Syahmi. And lastly, the application of ordinary differential equation in economics will be presented by Noor Amirudin. So I'll start off with my part, which is on the visual arts design and differential equation. Arts and mathematics are linked in a variety of ways. The application of mathematical skills in creating arts can be dated back to 50th century when Polycletos implemented the golden ratio of human body proportions in his sculpture. In this section of the presentation, ideas on how differential equations are used in creating, understanding as well as analyzing works in visual arts or design will be discussed. According to Britannica 2017, cycloid is a curve generated by a point on the circumference of a circle that rolls along a straight line. Because it provoked many disagreements among 17th century mathematicians, the cycloid has been dubbed as the Helen of geometers. In the late 1600s, Johann Bernoulli addressed the brachiostrokron problem and the cycloid was published as his solution. Suppose the circle has radius r and the point P starts at the origin. As the circle rotates through t radian, the distance it has rolled was published as his solution. Then, the polar equation to determine the parametric equation of the cycloid can be expressed as x is equal to r tau minus sine tau and y is equal to r minus cos tau. The most common definition used to be in terms of a differential equation. The cycloid is defined as the solution to the differential equation is shown in equation 3. To obtain the cycloid equation 1 and 2 are differentiated. To obtain dx over d tau is equal to r1 minus cos tau and dy over d tau is equal to r sin tau. Alternatively, we can also express cos tau is equal to r minus y over r. Therefore, the cycloid shown in equation 4 satisfies equation 3. Moving on to the application of the cycloid, the first one is in architecture. A number of modern buildings have employed the cycloid as a design element. In the Kimball Art Museum in Fort Worth, Texas, its designer Louis Kahn used 16 cycloid-shaped barrel vaults in 1972. The cycloid design was chosen by Kahn because of its gently rising sides that create the appearance of monumentality without overwhelming the visitors. Additionally, cycloidal arches were also used by Wallace Harrison in 1962 to design Hopkins Center for Arts in Hanover. The cycloid is also used in ornamental art of mechanical engraving. Machine patents were utilized on banknotes, stock certificates, and stamps for verification in the 19th century, as the artwork was particularly complex to be fabricated. Straight line ruling, the most basic of these security engravings, is based on a cycloid variation known as the prolate cycloid. Commercial banks in the United States were allowed to manufacture their own money before a national currency was founded in 1863, and the mechanical engravings helped persuade customers that the notes were real. The figure shows a close-up of the artisan banknote, illustrating the multiple prolate cycloids engraved on the banknote. Many forms of art, such as music, dancing, painting, architecture, and sculpture, contain mathematical elements. Each of these has a strong mathematical connection. It can be said that mathematics has given artists with a tool, such as the rules of linear perspective or descriptive geometry methodologies, among other ties to the visual arts. Differential equation particularly has contributed to the provenance of artistic arts. From the knowledge of differential equations, artists have successfully implemented the prospect of using differential equation beyond mathematics and science fields. Hence, inspiring various of mesmerizing works of arts and design as what can we see around us today. That's all from me. Thank you.
Assalamualaikum and hello everyone. My name is Ahmad bin Husairi. My matrix number is 207846. So for today, I will be explaining on how the ordinary differential equation can be applied in molecular biology. So before that, it is important that we acknowledge on how mathematical concepts has been used and applied towards other science-related fields using mathematical concepts such as molecular biology, bioengineering, and also medicine. So for the materials and methods on how the applications can be made is on first is important to analysis on the molecular biology problems such as genetic problems and all that, on how we are going to change it into a mathematical equation. To change it into a mathematical equation, it is important that the terms for the molecular biology names such as protein and such, it is expressed in terms of mathematical terms. So therefore, we can produce a mathematical equation from the molecular biology problems. After that, the equation can be derived and can be developed to turn it into ordinary differential equation, which makes it easier to understand the molecular biology problem. So for example, that I've included in the project. So this is the example. This is on how a molecular biology problem is expressed in terms of mathematical equation. As you can see here, this is the equation for hybridization of labeled nucleic acids. Is important to know that such as proteins are expressed in terms of X and Y, and also genes are expressed into lowercase x and y. So therefore, we will develop and produce an ordinary differential equation of the molecular biology problem. So next, I will be passing the next part of our presentation to my groupmate. So that will be all from me. So thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Noor Amirudin bin Azlan. My matrix number is 208062. I'm from Group 3. We present about application of ordinary differential equation in economics. The field of application of dynamic theory to economics is a vast and vibrant area. Application of differential equation are now commonly used in modeling motion and change in all areas of science. The dynamic theory has become an essential tool of economic analysis. An equation that involves dependent and independent variable and at least one derivative of the dependent variable with respect to the independent variable is called a differential equation. An ordinary differential equation contains two or more dependent variables with their differential coefficients. Principle of ordinary differential equations. As a rate of change on gross domestic product (GDP) xt over time, GDP is directly proportional to the current GDP itself, where T stands for time. Xt equal to Gxt. Bold X is equal to current GDP, and X is the previous GDP. Derivative is also represented by dxt over dt or prime t, while the growth rate of GDP is x over x, which is current GDP over previous GDP. If the growth rate g is given at any point in time, the solution will be xt equal to x exponent gt. Next, there is two types of ordinary equations. The first one is autonomous equation. Autonomous equation does not explicitly dependent on the time variable. For example, xt equal to axt plus v, which is current GDP equal to a is a parameter, xt is the previous GDP plus b also a work as parameter. Next, non-autonomous equation. For non-autonomous equation, it works opposite way of autonomous equation, where it's normally in both times and dependent on the time. For example, xt equal to xt plus sine t, where current GDP is equal to previous GDP plus sine t. Obviously, t is the main variable here. Next, application scalar linear equations on economics. The solution of the initial problem xt equals to axt or x0 xo equal to x0 is xt equal to x exponent at. It shows set of solution regarding differential equation for numerous initial value with a bigger than 0 and a is smaller than 0. Okay, for equation 1 is x plus utx equal to wt. X is the current GDP plus utx, previous GDP, equal to wt. Here is the graph for set of solution with numerous initial value. As you can see, if the a is bigger than 0, the graph will grow. Meanwhile, if the a is less than 0, the graph will decay. There's two types of differential equations. The first case is homogeneous case, where homogeneous case always comes with constant coefficient and constant term. It shown in equation 1. This is the equation 1, x plus utx equal to wt. When we substitute ut equals to a and wt equals 0, the solution will become x plus ax equal to 0 is xt equal to a exponent negative at, where a is an arbitrary constant. Next one is non-homogeneous case. For this case, it comes with constant coefficient only where x plus ax equal to b, current GDP plus a and previous GDP equals to b, where b is non-equal to 0. If a is equal to 0, the solution is xt equal to bt plus a. Meanwhile, if the a is not equal to 0, the solution will become xt equal to x0 minus b over a, x times exponent negative at plus ba. That's all from me. Thank you.